Our next presenter is Glenn Farris. He is the Vice President of Strategic Marketing for Universal Instruments. He's been in the electronics industry for over 30 years, starting as a research engineer at NASA, so probably cringes at the term rocket science, but when applied to electronics, but certainly has a lot of experience in advanced simulation technology, semiconductor test and measurement, and enterprise hardware and software platforms. So welcome, Glenn.
All right. Thank you very much, Ira, and thank you very much, everybody, for joining this very informative set of sessions here today and throughout the week. So the first two presenters did a very good job. Let's see if I can get my screen to move forward. There we go. The first couple presenters did a very good job talking about a lot of the challenges with heterogeneous integration, and particularly a lot of the things you need to think about from a design perspective. So I'm not going to go through too much of the detail on why heterogeneous integration and the diminishing of Moore's law. But what I want to do is talk about something a little different. We don't really talk about how do we really do the assembly of these things in the physical world? How do we most economically do the assembly of these multi-die packages in the physical world? And that's what I'm going to talk about in today's presentation. So this was already discussed, one of the issues being the fact that, when looking at looking at very complex SoC devices and very fine geometries, the costs of design have gone up, and this concept of going to chiplets could potentially, in theory, help reduce some of those costs. So what I'm going to discuss today is really two different ways of thinking about the assembly of these multi-die types of applications. One way to do it, which is the traditional way, is I have a single system that places a single particular die type. And then if I have multiple die types, I start daisy chaining together, if you will, multiple machines in a line to place each individual unique die type. Versus an alternative, which is something new in the marketplace, which is a single cell solution, in that one cell having the ability to place not just one unique die type, but being able to place a multitude of die types. And what I'm going to show in this discussion here today is that the single cell type of solution for assembly can result in much higher quality and higher yield. It can result in much higher throughput, in fact, versus for these multi-die applications due to the efficiency that you get through a single cell solution for multiple die. It can lower the other cost of goods, and it can improve the factory utilization, so that in the end, you end up with a much more economical solution versus a traditional single die per placement cell assembly solution. So what I'm going to talk about to illustrate this is a very simple example, and I'm going to go through a lot of different simulations, if you will, to explain the various parameters and the sensitivity of the economics to them. But I'm going to look at this basic conceptual device. So think of it as a substrate. The substrate could be an organic substrate. It could be a silicon interposer. It could be something that's actually a fan-out application at the wafer level or a fan-out application at a panel level. But I'm assembling multiple different die types together and integrating those into one package. And so I've called it the typical heterogeneous integration device. And if you look at that device that I've got there, let me turn on my little pointer too here. If you look at my little device here, I've got 4 devices, A, B, C, and D, and I've got 1 of device B, I've got 2 of C and 2 of D, and I've got 8 of device A. So 4 unique part numbers, and the quantities ranging anywhere from 1 to 8 in this theoretical or typical heterogeneous integration device. And then I've shown an example. Again, here is kind of to scale. This is an actual JEDEC tray to scale. And then in this particular application, I've just made up a a 30 by 40 millimeter device, or circuit, I should say, and then I've populated that with my devices, and I've populated that in a tray, and you can see I'm getting, it turns out to be 28 of these circuits in one JEDEC tray. So this is pretty typical. In the devices that we see, you typically have 3 to 4 different device types, and the device quantity can range from anywhere from 1 to 8. Okay. And what I'll show again, as I've said, in a cell that can do multiple dies in a single cell, you'll see that this allows for a very flexible setup and fewer operators and lower floor space, whereas this other strategy of having an individual machine placing each of those different die onto that next level substrate can have an impact on the accuracy. It can be very inefficient, and it can reduce the OEE and increase your overall cost. So how does that happen? So let's just say I've got my, I'm OSAT, I'm Joe's OSAT, and I've got 3 different circuits that I'm trying to build. One happens to have 2 part numbers. Another circuit that I'm trying to build happens to have 4 part numbers. And another circuit I'm trying to build happens to have 3 part numbers. And let's just, for simple sake, let's just say that I'm placing these in substrates in a JEDEC tray, and I'm placing all those die onto that substrate. So if you have a machine that is a single cell solution, I can pre-sequence those 4 part types on different wafer, that are all on a different wafer. And I can then, with that one machine, place each of those 4 types onto all those substrates before I am finished with that carrier and I move on to the next one. And another assumption that is being made here, of course, is that I'm doing an application where I need to pick these die direct from wafer. It's a case where the die are too thin to be handling them, putting them in tape and then picking out of tape or putting into some kind of a tray, but I've got a thin die that is very fragile, and I've got a cleanliness requirement because of the very tight pitches that's going to require more of a clean room type of environment, and I don't want a bunch of SMT tape and real applications or packaging in my assembly facility. So this one's simple. Okay, I do circuit 1, I use this machine. I do circuit 2, I use this machine. I do circuit 3, I use the same machine. Now, if I'm doing a single die per assembly cell solution, let's say I have circuit 1. Well, then I need 2 machines, and let's pretend that I do 8 die with one and 1 die with die B with system number 2. Okay, that's fine. But now all of a sudden I need to go to a circuit that has 4 part numbers. Well, now I need 4 machines. Or I want to do the circuit with 3 part numbers. Well, the optimized line would have 3 machines. But there's another problem. You can see I'm placing 8 die here and only 1 here. I'm placing 8 here, 2, 1, 2, 8, 4, 1. So this machine here at the beginning of the line, and it didn't have to be at the beginning, it could be at the end, but whatever the machine is that's placing a lot of die is going to effectively be the gate for this assembly cell, this assembly line. So this throughput of this machine, this first machine doing 8 die, is going to gate the throughput of the whole line. In other words, the second machine is going to be sitting here idle 7 out of 8% of the time. And the same kind of scenario happens in all these cases. So I have multiple systems, and I have either multiple line configurations to get the right number of die, which is problematic, but I also have a very unbalanced line, meaning one machine's doing all the work and the other ones are spending most of the time idle. Okay. So the multi-die solution, of course, in this case here, I'm placing all 4 die types in a single cell. I don't need to reconfigure if I'm doing 2 or 4 or 3 part numbers. And I don't have this need to have multiple different machines, and everything is done in one machine. So I, by definition, have a balanced line. So what are some of the economic impacts of that? Well, so first off, if I'm going through multiple machines, every time I do that in an assembly cell, what you do is you bring in your substrate, let's say. You normally will take that substrate. You want to make sure that it's perfectly flat and perfectly planar relative to the placement nozzle or the placement tooling that is placing the die. So I need to make sure that is all set up properly in the machine. If I now place one die and I now release that substrate and I now move it into another machine and I now pull it down flat again and I now make sure it's planar again and I now re-look at a whole nother, the FIDs, if you will, on the circuit again with a different set of cameras, I'm slowly but surely introducing greater and greater levels of inaccuracy and the potential to impact the yield because of that part handling and because of the vision finds that I'm doing. So that's problematic. The second thing I've talked about a lot already was the throughput. So the unbalanced line essentially causes idle cells in the line and therefore an unbalanced line and therefore very unfavorable economics. Obviously, the more die I'm doing and the larger the line, I've got more operators, I've got more floor space. That's increasing my operating costs for this line. And then the last one would be what I will call a low OEE scenario. And so this is where if I say, hey, I have one application that requires 4 unique part numbers and everything else is 2 or 3, I'm just going to build a line that has 4 machines. And then, some of those machines, I'll just pass the circuits through. I won't place any devices. I've got a very idle capacity from a line to device mismatch in that case. I also could use those machines to place the same die so I could try to get higher speed. But now I've got an inventory issue because I'm now moving these material across multiple different machines in the line. So in general, a problematic scenario. So I talked about the fact that in my simple example here, I had 28 substrates in this theoretical JEDEC carrier with my 31 by 44 device. So that's a JEDEC tray, today's JEDEC tray. In the future, there's a second generation JEDEC tray, which will essentially be double the size of today's JEDEC tray. So that will be able to handle 56 of these theoretical circuits that I came up with here. If you look at a wafer level fan-out application for a circuit this size, you would be able to put 38 of those circuits onto one wafer level substrate. And if I went to a semi-standard panel, so the 600 by 600 millimeter placement area, I could actually have about 247 of these circuits on that panel. And that's important because one of the things that you need to consider when you're looking at the economics of assembly is the impact of the carrier size and therefore the number of circuits that I'm placing die on before I complete the full circuit and move on to the next substrate. And that's because the one negative when you're doing this is you are exchanging wafers inside this system, and that does take a finite amount of time. So the amount of time that it takes, you want to amortize that over as many placements as possible. So it actually turns out that the larger the carrier, if you will, whether it's a JEDEC tray or it's a wafer level fan out or a panel fan out, the less time, if you will, per wafer exchange you are using per circuit in that particular carrier or substrate. So this is an important area to consider when looking at the economics of something like this, because it really has a significant impact on the overall economics and efficiency. The second point I mentioned was the yield. So again, if you have a single platform cell, the substrates come in, they are held down in place, they're vacuumed down. I look at all the FIDs once with the same set of cameras, and now I start all of the placement activity. And so typical PPM rates, so these are the defect rates in terms of placement in a cell like this, are going to be on the order of 100 ppm. If I now have 4 machines, and I'm now trying to build this same product in very high volume, but I've got the issue of my substrate curvature where I bring it in, I flatten it out. I place everything, I let go, it curves, I move it, I flatten it out again, I place the next die, I move it, I flatten it out again, I place the next die. There's going to be movement of those die from the curvature, the flexing of the substrate. There's going to be movement of those die potentially just from the movement of the substrate in between carriers before I've formed a permanent bond. So that's going to create some level of placement error. Secondly, the vision finds. I don't have a common vision find reference. I'm going to have greater FID location variation. I've got a different set of spindles. I've got a different machine. Every machine has its own little peculiarities to it. And so think of it as increasing the number of the population of spindles that are placing from a small number to, let's say, 2, 4, 8x the number of spindles. It's going to increase the variation of placement, and therefore it's going to reduce the yield. So in this case, if I end up with effectively that 100 ppm defect rate in each of the machines, and I have 4 machines, it's going to result in about a 0.5% yield loss, which is a very expensive proposition, equal to about almost $400,000, $340,000 a year for a 3-shift operation if the total circuit I'm building is about $50. So message here again is from a yield perspective, you really want to do everything in a single cell where I hold that substrate down. I do all the placements. I do all the FID finds one time in one place. And then when everything is complete, I move those circuits out of the placement tool. Next area, again, just thinking about the fact that I have either 1 or 4 machines in that multi-die single cell machine, I'm going to be fully utilizing the cell at all times because I don't have a cell that is sitting around waiting while another one's working very hard. And the big issue, again, is going to be how do I minimize that exchange time from one wafer to another as I'm changing from the die A on wafer A to die B on wafer B. I have to take one wafer out of my wafer table. I have to put another wafer into that table and change all my tooling automatically and then start the placement. So I need to be able to amortize that time. I'll show you some numbers in a minute, but bottom line is if I have 4 die types and I do 13 placements and I have 32 substrates as a mathematical example, you'll see, and I'm going to show you that the single cell throughput is about 60% higher for that application. So what I did is I said, okay, let's go do some sensitivity analysis. So I mentioned this particular case here on this last slide. For 4 die types, 13 placements in total, 32 substrates, I had 60% throughput improvement with a single cell machine. So what happens if I start to vary things? So what this chart is showing you is if I go from 2 unique die types to 4 and then to 8 unique die types. So that's what's on the horizontal axis. The vertical axis is trying to plot what's the per cell throughput ratio. Another way to think about it is how much lower in cost would the multi-cell machine need to be in order for the economics to be equivalent to the single cell solution. So for example, that point at 2 unique die types up at the top at 40%, it's saying that if I was doing 2 part numbers and I placed 2 of part 1 and 1 of part 2, that's the 2-to-1 placement ratio for a single bay that you see up here. This point says that the single die machine would need to be priced at 40% of the price of a multi-die machine. So then what I've done is the colors here are representing different ratios in terms of the number of die for the die that has the largest quantity to the number of die for the smallest quantity. So I talked about this case here. This was 2 die with a 2-to-1 placement ratio. So now if I go 4 die with the 2-to-1 max to min placement ratio, or 8 die, same thing, you can see how the economics improve with the single cell versus the multi-cell solution for this. And then looked at it where the ratio of die is 4-to-1. So 4 of the highest quantity unique die and relative to 1 for the least quantity device. And you can see that the numbers drop from kind of this 40 to 35 to a 30 to 25 range. And then if I go to 8-to-1 placement ratio, it gets even better. And this is using a case where I assumed that I had a single wafer table. So I have 1 wafer table and I'm exchanging each of those unique wafers in and out of 1 table. The charts here in the lower section is the exact same analysis for the same 3 scenarios, a 2-to-1 a 4-to-1 and an 8-to-1 die count ratio for the different unique dies. But in this case, I assumed that I could have a system where I had 2 wafer tables in the system. So it's cutting the number of wafer exchanges in half. And in that scenario, you can see that you range from anywhere from the single die machine needing to be about 10% of the cost of the multi-die machine to around 15%. So it's sort of 1/6 to 1/10 the cost. So I did another analysis. In this case was to say, okay, so that gives you an idea in the last slide of how the number of die types and the ratio of the die quantity impacts the overall relative economics. In this case, what I'm doing is now looking at, okay, what if that time that it takes to exchange those wafers is varying? In the previous slide, I didn't mention it, but the number was actually based on a 40-second time. So it was this time right here, 40 seconds. Well, let's say the time got worse and it took a whole 60 seconds to exchange a wafer, or maybe the time gets better and I can get it all the way down to 15 seconds to exchange a wafer and to exchange all the tooling in the system. So that's what this horizontal part of this table is looking at. Is it's a variation in the wafer exchange time. In the example on the previous table, as I mentioned, that was assuming I had 32 circuits in a carrier. So what I did here in the vertical axis is I'm now saying, well, what if I don't have 32 circuits in a carrier? What if I only have 4? Or maybe I go all the way up to 1,000. Remember, in a JEDEC tray for this kind of 30-ish by 40-ish millimeter circuit, I was in this 16 to 32 range. As I go to wafer level, I'm kind of just not a whole lot more actually wafer level fan out. I'm in this sort of 60 range. And if I went to a panel fan out, I was in the 250 to 300 range. So you kind of get an idea for the different types of typical carriers, the number of circuits I might have. And you can see that very quickly, even at 60 seconds and only with 4 carriers, the economics are about the same. As I move down to very fast wafer exchange times, and as I move to a very large number of circuits, I get even way lower numbers than I was getting when I was assuming 32 and 40 seconds, obviously. So I get all the way down to cases where even in the single wafer table example, the cost of a machine that is a single die placement tool would need to be less than 1/6 the cost of a machine that is a multi-die capable tool when I have a single wafer table, and it gets down to less than 7%. So it's almost 15 times less expensive in the case of a dual wafer table if I'm doing very fast exchange times, if I'm capable of doing that, and if I'm doing a very large substrate like you would see in a panel fan-out type of application. So a very substantial reduction in the number of, in the overall cost for the assembly solution. So that's my analysis in terms of sensitivity. Just again, as a reminder on some of the other points. So in the single cell, I now have one machine and I really don't need more than one operator. One operator can certainly run that complete cell. It's fully automated. All the tooling is exchanged automatically. The recipe is downloaded. It's really just monitoring that system. And it's one machine as opposed to, let's say, 4. So I've got much lower floor space. So much lower overall facilities and operational costs. In the multi-cell case, if I've got 4 machines, potentially I could need as many as 4 operators. If I had 8 machines, maybe I need as many as 8 operators. Might not need all those operators, but you're certainly going to need more than in the single cell case. And I've certainly got a much larger line and a much larger overhead expense from the factory. And if you kind of take the 4-to-1 case, this could result in about almost $750,000 of additional other COGS per year, assuming a $38 per hour fully burdened factory rate. The last area I want to mention again and reemphasize was the fact that I have a machine that is always fully utilized when I'm doing a single cell versus a multiple cells each doing a single die. So if I look at that and I just do some kind of random numbers, simulation, assuming I have 4 or 5 different products I build in my factory, each with different numbers of die types, you could see that you might see a 30% utilization drop per line if I had 4 lines that were dedicated to 1, 2, 3, and 4 different part number type assemblies. And that would, again, lower my OEE and have an impact of about $90,000 a year. So what I've done here is a little economic model using that, fixing the 4 die scenario, 4 unique dies with a 4-to-1 ratio. And what I'm trying to show is a full summary of the economics of the single bay, single cell versus the multi-cell alternative, which compares, again, everything placed in one machine versus one machine placing a single die and stringing those together. So in the first case, the cell efficiency is much lower for the multi-cell alternative. The number of circuits are balanced. I'm doing the same number of circuits. I've built this up so that I have the same circuits per year. And then I've come up with I've made up a number just as an example, okay, for a solution price for one single cell machine, and then in the other case for 4 of the multi-cell machines. Using a 5-year depreciation, and I get a depreciation cost. I've then looked at the cost of assembly. So looking at the impact of the defect rate, the placement defect rate. So what is that from a circuit yield loss and from a throw rate perspective? What's the overall total scrap cost that I get out of the machine because of that higher DPPM rate in the machine? The utilization based on the fact that I've got the single cell that I have to maintain versus having 4 cells I have to maintain. And then the operator cost. So going from 1 to 4, and I get a cost for that for the operators, and then additionally for the floor space. So you see in this particular example, just as an example, that the single cell, single base solution results in a very substantial improvement in the economics of about 3 to 1 basically. The last point there is to say, well, let's say that we don't know what the cost of these machines are going to be. Let's just say that I could get all of my machines for free in the multi-die or in the multi-system case where I placed a single die per machine, and that those machines were free and I only had the ancillary costs. You still see that it's more than a 2-to-1 variation in terms of the overall cost, that you have about a 60% lower cost per device assembled with this single cell solution capable of doing multi-die placements. So that's what I had. Questions from folks?
Thank you, Glenn. Good presentation. A few questions. How are the die presented to the single cell? Are they on wafer, on tape? What's the input to this multi?
Yeah, in both of these cases, this is assuming that I'm placing from wafer. This is I have to pick the die from wafer. They're very thin die, and therefore I can't put them in tape because they're going to be damaged, or I can't use tape because I've got a very clean environment, and that's not going to be acceptable in that environment. So I'm doing a direct from wafer pick.
Okay, but it's an already diced wafer, so it is on a frame with tape behind it.
Correct.
Okay,
Yes.
got it. And I assume then the machine needs to know the wafer map, so it knows which die to skip and all that kind of complexity.
Yes, you've got to be able to handle multiple wafer maps. You've also got to be able to handle multiple different sets of tooling, because I've got different die sizes, and so I need different pick and eject tooling in the machine, and you need to be able to exchange those as you transition from wafer A, let's say, to wafer B.
Okay. Got it. Okay. And then, I was just looking at this, and, Pane Vecchio, or Intel's Pane Vecchio, which is now called the Max, has 47 different die on it. I haven't seen the die breakdown, but it's easy to imagine as people continue disaggregation of chiplets that you might have more than 8 types of die you need on one substrate. So what happens in that scenario? Do you put 2 multi-cells together?
It would depend. So if you have, depending upon the die sizes, right? If you have a die size that can use the same set of tooling, so the same set of ejectors and pick heads, then you could do more than 8 in a single cell. If not, then yes, once you went beyond that point of needing more than 8 unique sets of tooling, then you'd need a second cell in that case, yes.
Okay. But does this tool have then like 8 boats loaded on it or something with the different wafers? Or, I mean, so you're going to have to interleave. It just, the complexity is going up pretty quickly as people disaggregate.
Yeah. So what you have to do is you have to come up with a very, unique concept for doing that. So what this particular tool does is it takes those wafers and it puts them in a cartridge and pre-expands them. So now I've got pre-expanded, ready to go cartridges that I'm able to exchange in the wafer table very rapidly.
Got it. Okay. And in terms of assembly, one of the questions that came in is, does the yield, or maybe more accurately, the defects grow linearly or exponentially as the number of die go up? And obviously we're talking about placement accuracy, not die quality, sort of.
Right. I don't think that, I'd say that the jury is still out on this. There's not enough high volume applications yet to know for sure. I think that at a minimum, it goes up linearly. It might go up more than that. It might go, I don't know that it would be truly exponential, but I think it's a minimum as a linear impact.
Okay. All right. And then related to this, there's another question is, what after dicing and thinning, and I'm assuming you're doing some type of inspecting when you pick the die up. I mean, is there some threshold where, the economics break down? If the yield is too low after the thinning and dicing, or, I mean, is there some sort of benchmark yield that you normally expect? I mean, are we?
I haven't done that analysis, so I can't give you an exact number, to say where does that start to really impact this. Certainly, if you had, 5 good die on a wafer, that's not going to work. You're not even going to be able to build a circuit, and you're going to be exchanging wafers all the time. So, but that would not work for any scenario, right? But in terms of a comparison of a multi-die versus a cell versus a single die cell, that's something to be analyzed, because typically we're looking at hundreds of die on a wafer and we're not really too concerned, whether it's a 70% or 60% or 90% yield. That's not going to make a difference. But if it's a very large die and I'm really starting to impact how long it's going to take to exchange a wafer, it could have an impact.
Got it. Okay. Got it. Well, good. I think that's all the questions. I thank you very much, Glenn. And once again, I would like to thank our lead sponsor, Advantest, rated as the #1 supplier of semiconductor equipment in 2022. And our other sponsors, Amcor and Cadence, their sponsorship has made this event possible and free of charge. So when you have an opportunity, please thank them. And I thank all of you for joining us today. And we look forward to seeing you tomorrow. Have a good rest of your day.